All right, I hope everyone had an opportunity to do the homework. I I posted the solutions to the homework yesterday. Um, I want to start today off. I'm not going to answer questions on the homework because the answers are on the web. So if you look at that and you still have a question, we can meet up and talk about it. But for now, we're going to get into today's material. Um, Come on. Everyone get your calculator out if you have a calculator. I'd like for you to quickly, on your calculator, figure out what your calculator says e to the second power is. Everyone figure out what e squared is on your calculator. Well, approximately. So 7.389, 0.56, right? Something like that, right? And keeps going. All right, so I'm going to say approximately. Well, it turns out, see if I can write on this. It turns out that, and this is where we're headed, okay, in this class, that e to the x can be represented as a power series. And the power series is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. We talked about this a while back. Do y'all remember me doing this? Yeah? So I'd like for you to plug in just into this formula. Now this is plus dot 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 forever. Plug in e squared. Just so on your calculator, you're going to have to do 1 plus 2 squared over, what's 2 factorial? 2 times 1, which is 2, plus 2 cubed over what's 3 factorial? 6, plus 2 to the fourth over what's 4 factorial? 24. So do 1 plus 2 plus, what, 2 again? Isn't 2 squared over 2, 4 over 2, so that's 2. This is 8/6, which you can, 16 over 24, you can reduce those. Someone get those, just those fractions there. Do 1 plus 2 plus 2 plus 8/6 plus 16 over 24, and what do you get? 7. Even? Oh, it's 7? It's just 7? We got lucky. Okay. Let's go one more term out. Let's go, what do you think the next term in that sequence of terms is, the power series there? X to the fifth over 5 factorial, which for us would be, what, 32 over, what's 24 times 5? 120? So add now that term to it, and what do you get? 7.533? Wait, 7.5? Yeah, it shouldn't be 7.5. 7.2? Anyone else get 7.2? So look, when we stopped at 16 over 24, we got 7, right? When we went one more term out, we got 7.2, right? If we go another term out, we're going to get even closer to what the approximate answer was. What was the approximate answer? 7.389, right? Your calculator, when you type in e squared, your calculator is actually doing this. It's doing this arithmetic here. It's just stopping at some point. And if you want it to go further out, you want to get more decimals, it'll go further out. Does that make sense? So every function can be represented, well, almost every function can be represented as a power series. So I have a little graphical thing to kind of show you this happening. Let's see how this works. Let me get down to, I don't think I have e to the x here. Okay, can y'all see this function? This is the function 1 over x. Wait, no, not 1 over x. 1 over 1 minus x, all right? Where the hell's my pointer? There it is. We are going to see, one of the first things we do today, we're going to see that 1 over 1 minus x can be represented as a power series. So it's going to be something plus something plus something, powers of x forever, right? Right now, you can see the red is the 1 over 1 minus x. That's the red one. This red vertical line is an asymptote, so just ignore that it's even there. This black line is this function 1. So does 1 look like that function? Like is that constant 1 function a good representation of that? Not even close, right? Not even close. Do y'all see what I'm saying? Like as an approximation, that sucks. Now, then watch what happens here next to the 1. The next term in that series, because I said we're going to be able to represent that as a power series. If we do 1 plus x, we get this line. Is that closer to that red picture? It still sucks though, right? It's not very good. Now, the next one is going to have an x squared in it. Now this is a parabola, isn't it? Is that black parabola a better approximation to the red one? It's better, right? It's not perfect. It's better, right? Now the one that we did before, I left it behind just so you can see that our approximation has gotten better. If I go again, now look at this black one here. You see it right here? Now I'm going to start cranking them out. See all these powers and start coming up. See, watch what's happening. See how we're getting better approximations in here? Yeah, but do you see that my black one is almost laying right on top of that red one now? Almost. Now over here, it's not good at all, is it? Like over here, I'm not even close. Well, the reason why is because this series right here has a radius of convergence of 1, which means if you look at 0 to the left one and to the right one, my series right there, that series of power functions, is a good approximation to the 1 over 1 minus x on the interval negative 1, 1. Outside of that, it's not. Get what I'm saying? So let's try and look at something else. Here's e to the x, right? There's e to the x. My first term was 1, right? If I just use 1, that approximation's terrible. If I use the next term, which was x, that's a line, that's still terrible. Here's the x squared over 2 factorial, right? If you do those together, it's a parabola. That's better. Better, 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 better. You see that? But now what's happening is I'm staying pretty darn close as I go out, right? That's because the radius of convergence of this one is infinite. It converges for everything. Like in your homework, you should have had a problem where it said, what's the radius of convergence? And it converged for all x. If it converges for all x, that means there is no interval. It converges everywhere. The radius is infinity. Now I can zoom out to kind of show you. I'm going to zoom to the left here. That if I keep going, my black one keeps on sticking onto this. Now I'm starting to slow my computer down because it's having to draw all this. I think I brought it to its knees there. Okay, I'm just going to let it be. I better plug in. But do y'all see how we have this power series that is an approximation to e to the x? And the further you go out, the better it is. And if you could go out forever, it is e to the x. Make kind of sense? All right. And we can do this for a lot of different functions. Here's e to the negative x. I bring this one up because e to the negative x is a function that it's a classic example of a function that you cannot find the antiderivative of. Like, there's no way you could try all your different techniques of integration. Integration by parts, trig substitution, everything, partial fraction, anything. Throw it at that, you'll never be able to get the antiderivative. It does not exist, okay? But it can be expanded as a power series. Now look at this one. This one's pretty cool. See how those are starting to fit onto that graph? And again, the radius of convergence for this is infinite. So what we're going to learn today is that if you are trying to integrate this, right? If you're trying to integrate it, you can't do it with any technique. But if you rewrite the e to the negative x squared in its power series representation, then you can integrate these term by term. And you could get as close to the real answer as you'd want to. Okay, so if someone wants you to integrate from 0 to 1, all you'd have to do is do integrals of each one of these 0 to 1, 0 to 1, 0 to 1, 0 to 1, as far out as you wanted to get the precision that you needed for the problem. Make sense? I'm not going to get into that, but, well, I guess I will. You remember we had power series about the number a? Remember that in the formula? We called it the power series about a, and it was x minus a in the formula. Well, I can move that a around, and if I move the a around, what will happen is, darn it, back up. Let me go back up to this example right here. Notice in this example, it took me a long time to get close to the real answer over here. Like, I had to go through a lot of actual steps to actually get out to that one, to get close out here. And if I wanted to be really close out here, I'd have to do a bunch of those, wouldn't I? Well, if I change my a in the series, so if I change, this is the a, it's that dot. If I slide it around in the series, I can actually make it converge to it faster. Watch. If I go over here, remember, I'm trying to get close to that, right? See how many iterations it takes. I'm already close, right? See how I'm already pretty much dead on here? Where the other one, it required a lot more. So as you move a around, if you're focusing on one value of this function, you move your a towards it and you can get to it faster. You can converge to it faster. But of course, it changes all your power series. Sine cubed x. Another example of a function that you cannot integrate. You cannot integrate this function with any method we've ever learned. There's the function right there. Here's the power series expansion. So here it is. The black one's coming in here. Give it some time. There we go. See, my black one's starting to fall in line with the red one pretty good there. Okay, so you see it happening? This is just a visual to help you see what, the power of the power series is going to be. It's going to be a way for us to represent functions that would otherwise cause us trouble. That's it for that. All right, I'm gonna call today grown-up math time, grown-up math day. All right, you're gonna learn a lot about notation and series today. What? Yeah, but today's this section is tough. Put your big girl pants on. I don't want to be sexist and say big boy, I mean, let's get all genders involved here. All right, 8.6. I'm going to do this like I did last class. I'm going to present the notes on the board, and then when it comes to examples, they're already written out here, but I'm going to do them on separate paper. And we will start with title of the section, representing functions as power series. So now what we want to do is we want to be able to take a function and write it out as a power series as opposed to just the function. And the first thing I ask you to remember is that with the geometric series, remember the good old geometric series? A plus AR squared plus all that? We said that that converged to A over 1 minus R as long as the absolute value of R was less than 1. And this right here, this sum, is the way of representing that. And I actually want to erase and make it a little bigger so you can really see this. It's the sum starting at n equals 0 to infinity of a r to the n. So what happens when I start at 0? I get a times r to the 0. What's r to the 0? 1. So a times 1 is a. The reason why I'm doing this is because the first time I showed you geometric series, we started at 1. In the formula, see I wrote it over here in the corner? We started at 1 to infinity, and instead of having ar to the n, we had ar to the n minus 1, didn't we? But do you agree that this creates the same thing as this? Because if I start at 1 here, I get a 0 from my first power of r, which is the exact same thing that happens here. Do y'all see that difference? But they're the same.
If you started at 1 on the one on the top left,
If we start that,
it
would be geometric, but it would not converge to this because if you started this at 1, your first term would be AR, then AR squared, then this, right? So it would be, you would be missing the A. So it would be this right here minus A. Because you'd be missing A. So you have to take it away from that sum. Does that make sense? Okay. All right, so now, if we replace the A in the problem with 1, and we replace the R with X, then we get 1 plus X squared plus X cubed forever. Agreed? And that should turn out to be A over 1 minus R, which is going to be 1 over 1 minus X, as long as the absolute value of X is less than 1. So do y'all see all I'm doing is taking the geometric, giving a specific case where A is 1 and R is X, and we get this very, very nice big, I say big time, okay? Big time means this is going to be used a lot, today especially. And I wrote down the sum in the left. I'm going to rewrite it a little bigger. Sum n equals 0 to infinity of x to the n. And you can check it for yourself. You let n be 0, x to the 0 is 1. Let n be 1, x to the 1. Let n be 2, x squared. N be 3, x cubed. And you keep adding up forever. So if you add all these powers of x up, it will converge to this, as long as the x's are less than 1. You ready to do a problem? Let's do one. I would like for us to express this as a power series. I'll rewrite everything. Express let's call this example 1, okay? Express 1 over 1 minus 3x as a power series. The only thing we know right now is that 1 over 1 minus x equals 1 plus x squared plus x cubed plus forever and ever if the absolute value of x is less than 1. That's what we know, right? That's the only thing I've given you today.
Yes.
So how can we look at this right here and see that it's somehow connected to this? Well, I can make this substitution. Let's let u be equal to 3x. Okay, now this isn't like a substitution like integration, okay? I'm just making an algebraic substitution. Everywhere I see a 3x, I'm going to replace it with a u, right? So how would you rewrite this then? 1 over 1 minus u. And according to this blue part, that turns into what? 1 plus u squared plus u cubed, as long as what? The absolute value of u is less than 1. Agreed? Now, what was u? 3x. So this becomes 1 plus 3x plus 3x squared, 3x in parentheses squared, plus 3x cubed, right? Plus dot, dot, dot. Yes? If the absolute value of what's less than 1? 3x is less than 1. But that's the same as saying 3 times the absolute value of x must be less than 1, which is saying the absolute value of x must be less than 1/3. So I just did a little solving for absolute value of x here. Isn't that a power series right there? Isn't that a power series representation of the original problem? Okay. We want to be able to write it down like this, but we also want to be able to write it down in its sigma notation. Sigma notation. So what I'd like to do is approach the same problem with a slightly different tactic here, all right? What I'm going to do is I'm going to write down the original problem again. It was 1 over 1 minus 3x, right? And below it, I'll write down in red what we know. 1 over 1 minus x equals 1 plus x squared forever, right? But what was that written as a sum using the sigma? Sum n equals 0 to infinity of x to the n, right? Okay, this is the formula we know already walking into this. But instead of having x here, right? Instead of having x, what do I have? 3x, right? So I could write this as 1 plus 3x plus 3x squared plus dot, 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 which equals sum n equals 0 to infinity of what? 3x to the n. So this highlight in yellow in this box here, that is the power series for this expression. This is it written out in sigma notation with that sum. This is it written out just with dot, dot, dots. Questions? So far, everything seems nice, right? No big deal. It's the calm before the storm. Example 2. Same instructions. Express this as a power series. Does that look anything like what we just did?
Looks like it, yes.
What would you say the big difference is?
A equals 3 plus 5.
We have a plus, not a minus, right? And we have a 3 in the numerator, where in the formula we had a what? A 1? Yeah, so can't we just do this? Can't you just say this is the same as 3 times 1 over, now watch me be tricky here, 1 minus negative 5x? Isn't this the same as 3 times 1 over 1 minus negative 5x? Now, if I take this negative 5x, that's kind of like the 3x was in the previous problem, isn't it? So I'm going to go straight to the sigma notation answer from here. This equals 3 times sum n equals what? 0 to infinity of
Negative 5x.
-5x to the n, right? Agreed? Now, I could ask you at this point what the radius of convergence is, right? And then you'd have to do what the previous section's homework was all about. You have to do ratio test on this, check at your endpoints. All that stuff would have to be done if. So that's the way these questions in this section are going to appear. Rewrite this as a power series, find its radius of convergence, find the interval of convergence. Done. Their problems are pretty long. Okay, now this is it so far, right? I want to just ask you if these are the same. Okay, I mean we could be happy just the way it is right now, but I want to make sure you understand some of the things you can and can't do with sums. So can I put the 3 inside there?
No.
Can I put the 3 in here next to this, like 3 times all that? Isn't this sum, like after this dot here, isn't this sum like something plus something plus something plus something forever? Right?
Yes.
In parentheses. So couldn't you distribute a 3 to each of those terms? Right? No? No, like if I wrote this down here, 1 plus x squared plus x cubed plus dot 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 dot, and I came in with the 3, wouldn't that 3 be able to go to each one of those like a distribution? Like 3, 3x, 3x squared, 3x cubed, right? So putting a 3 in front of each of these is equivalent to distributing it through, isn't it? So moving that 3 inside is okay if this is multiplication. So I can write 3, now is this okay? Times 5 to the n times negative 1 to the n times x to the n. I'm just asking you if this is okay because of where we're headed today. Is that all okay? I mean, this n is basically a power on all of this, right? It's a power on negative 5 and a power on x. And negative 5 can be written as what? Negative 1 times 5. So I can put the power on the negative 1 and on the 5. Now, can I put these two together and say 15 to the n? No. Because exponents would always have to be computed before you could do the multiplication. So that's okay, right? So you could do ratio test on that, couldn't you? Yeah. Okay, I just want to make sure you're comfortable with the changing things around. Now, what if I asked you to write out the first six or seven terms of this series? Which one of these do you think you would look at? Probably this one right here, right? And just start plugging things in. So let's write out a few of these terms. Let's let n be 0. What do you get? 3. Good. Okay, let's let n be 1. So negative 5x to the first power is negative 5x. Multiply it times 3. Negative 15x. Yes? What's next? Let n be 2. What's negative 5x to the second power? 25x squared times 3, which would be plus 75x squared. Next one, you could go and get more, right? Next one would be negative 375 x to the third plus dot dot dot. You should be comfortable both ways, okay? You should be comfortable doing it here or here. Hey, just FYI, okay? Dot 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 is accepted mathematically. It's not like I'm just being lazy, but it's normally 3 dots represent continuation of that pattern. Like it's not just like as many dots as you want. It's usually 3 is what we use. Sometimes you'll see me use 4 or 5, but 3 is that's the convention, all right? If you want to be a rebel and go out and do 4, you know, live on the edge, go for it, man. Okay, next one. Ready for our third example. How does this seem so far, though? It's all right? You're right. You're right. Okay, example 3. Same thing. Expresses a power series. 5 over 4 plus 3x. Notice anything different in this one? So in the last problem, we had something other than 1 up here, and it was okay. We had something other than x here, we were okay. It was plus in the last one, we were okay. But in the last one, that was a 1, wasn't it? And in our formula, that must be a 1. So now it's time to play a game. All right, so tell me if you believe this. This is the same as 5 times 1 over 4 plus 3x. That's right. But that's the same as 5 times 1 over 4 times, in parentheses, 1 plus 3/4 x. So essentially, I'm factoring a 4 out of this. Factoring a 4 out. So if you factor a 4 out of 4, you get 1. But if you factor a 4 out of 3, you have to create something to kill it off. So you have to basically put a 1/4 in there. Is everyone all right with that? That's something that's just kind of like should be like knowing how to use a hammer. You know, everyone here knows how to use a hammer. Everyone knows how to factor a 4 out of something like that. Okay. All right. Now does that look like? Let me see. How about that 4 comes out completely, goes underneath the 5? And then what should I do on the bottom? Minus a minus. 3/4 x. And now we finally have it looking like our big time formula, right? And now we go to town with this. I'm going to go straight to the sigma notation, which means sum n equals 0 to infinity of what? Oh, 5/4 I put outside. Negative 3/4 x to the n. Rock and roll. Let's write out the first few terms. If n is 0, what do you get? 5/4. Okay, if n is 1, negative 3/4 x to the first power times 5/4, which is negative 15 over 16 x. And then? Yeah, 45 over 64. It'll be positive x squared. Okay? Again, on all these problems, you could be asking for radius of convergence and interval of convergence. I'm not doing any of that because that was homework from last class. Are y'all happy or not? I mean, is this all right or? Okay. We turn the screws. Oh, not are you happy? I guess I shouldn't say that. Are you happy? I mean, really, like deep down, are you happy? Don't just give me some, yeah, everything's great, life's great. I mean, are you happy? You sure you don't wear that smile to cover up a broken heart? All right. We're losing it, man. The end of the semester is upon us. I can feel it. How many weeks do we have left? I don't count. That way I'm excited when it's like next week's or last week. No, we have what, 2 weeks and then finals? So we meet 4 more times after this. All right. Look at this one. Yeah, uh-oh. You're not happy? Any ideas? Pull out what? Yeah, why not? Pull the x to the fifth out front as multiplication times 1 over what? How about 2 plus x, like that, right? Now, pull out a 2 so you can get a 1 down there. So here, I'm going to put x to, I'm going to go a little slower than that. I'm going to go 1 over, I pull a 2 out. If I pull a 2 out, I get 1 plus 1/2 x, right? And then I can pull that 2 in front with the x to the fifth. I'm just going to put it as a 1/5 out there. Times 1 over, last step here, 1 minus negative 1/2 x. And now we get it to match up exactly the way we want it to. So this equals, now what's sitting in front is still the 1/2 x to the fifth, right? But now this part turns into sum n equals 0 to infinity of negative 1/2 x to the n. Which equals sum n equals 0 to infinity 1/2 times x to the fifth times 1/2 to the n times negative 1 to the n times x to the n. Is that right? So all I did was because I had a negative, right, I looked at that as a negative 1 to the n. Because I had 1/2 in there to the n, I have 1/2 to the n, the x to the n. But then I put the 1/2 inside and the x to the fifth inside. The reason why that could go in there is, again, because x to the fifth is just like a number. It's going to be distributed to each one. So you can put it inside the sum. As long as this is multiplication in front, you can do that. That's right. Now I'm going to put the x to the fifth and x to the n together as x to the 5 plus n or n plus 5. Remember, if you have the same base, you add exponents, right? What else can I put together? How about the 1/2s? How about the 1/2s? Isn't that first one 1/2 to the first power? So what's 1/2 to the first power times 1/2 to the n power? N plus 1. So I get 1/2 to the n plus 1. I still have that negative 1 to the n. And then I have the x to the n plus 5. Is that what we said? Questions? What?
I wasn't paying attention when you were doing the last part.
So are you okay with this step? 1/2 to the first power, 1/2 to the n. So we put those together, you add the exponents. So it becomes 1/2 to the n plus 1. And then the same thing on the x's. X to the fifth plus x to the, or x to the fifth times x to the n is x to the n plus 5. And then you can do ratio test on that. And do we want to write out a few of the terms or not? Yeah, let's write out like 2 or 3 of them. So this would be equal to, let's let n be 0. So 0 here we get 1/2, 0 here you get 1, and then 0 here you get x to the fifth. So 1/2 x to the fifth. Yes? Okay. Now let n be 1. I'm going to change signs, right? If n is 1, so you get, yeah, because n is 1, that's going to give me a negative 1. N1 here gives me 1/2 squared, which is 1/4, x to the 6th. The next one is going to be 1/8 x to the 7th minus 1/16 x to the 8th plus dot dot dot. Okay, one more example and then the wheels are going to start coming off, all right? Maybe they'll start wobbling. Which example are we on? That was example 4, we're example 5. I'm numbering them because I'm going to refer back to some of these later. Okay, same thing. Find the power series. Express this as a power series. I need to get a different headset. This thing is a pain in the butt. Okay, so 1 over 1 minus what? Negative 1x to the 5th. Can I just go negative? Is that the same thing? That's the same thing, right? So I'm not trying to trick you on this one. I mean, it's just want to make sure you understand that that it can have powers down there. You can have like x squared down there and look at it as 1, minus x squared or whatever it is. So if we have x to the 5th down there, we can look at it as 1 minus negative x to the 5th. And then just go straight to your sigma notation. N equals 0 to what? Infinity of negative 1 to the n x to the 5th to the n. So you see, because it was negative x, I already know that's like a negative 1x, right? Or negative 1 times x to the 5th. So I already peeled that negative 1 off in front. And then x to the 5th. Now I could go one more step if I wanted to. What's x to the 5th to the n? X to the 5n. Because there's where you multiply the powers, right? And let's write out a few terms. If n is 0, you get 1. If n is 1, you get negative, what? X to the 5th. Plus, if n is 2, x to the... Did I lose everyone or what? Did I lose you? No? What's wrong? So we're good? Oh, okay, all right. Just want to make sure. Dot, 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 dot. Freaking rebel. All right. That's it. Those are our first examples. So you can see how powerful that geometric series is at allowing us to rewrite some things as series, right? Now, oof. Yes. There's no always. If you're checking your answers in the back of the book, they a lot of times pull the negative out. But if you were to have left it in there, it wouldn't be wrong. So, not necessarily. When you go to ratio test, it's good to have the negative 1 by itself because you know that it's in ratio test and the absolute value is going to go away anyway. So if it's a negative 5 still, you have to account for the 5. So, you know what I'm saying? I mean, but that would be the only reason at this point. Okay, some more notes here. We need to get back to... So I think I've worked through all these. Let me see. Yep, okay. Now, we talk about what is called term-by-term differentiation and term-by-term integration. You'll remember, and I'm not going to write this on the board because this was Cal 2. Remember, wait, Cal 2. We're in Cal 2. All right. That if you want to do like antiderivative of x plus 2, right, two terms, that you could just do antiderivative of x plus antiderivative of 2. So you could split it up into 2, right? So if you have two terms, you do integration term by term. Now, we never did that. We just went 1/2 x squared plus 2x plus a constant, and we were done, right? But this was the idea. That was a property. You could split the integral up into two integrals if it was a sum or a subtraction. If it's multiplication, no go, right? So what this theorem says is that if we have a power series, now remember a power series is written where you have a c sub n, that's a number, right? In front of powers of x that keep getting higher. I also want to add something to this. It should start at n equals 0 and go to infinity. That's our power series. So if you have a power series and it has a radius of convergence, which is some number that's bigger than 0. So it does converge somewhere is what that's saying. On some interval it converges. Then the following are true. First of all, you can call this power series a function, f of x. And what it is just writing all these out. So you plug 0 in first. If you plug 0 in, what do you get? C sub 0, right? Times x minus a to the 0. What's anything to the 0? 1. So c sub 0 times 1, which would be c sub 0. Then you plug in 1. C sub 1, so some other constant, and then x minus a to the first power, which would be the second term. And then c sub 2, x minus a squared. C sub 3, x minus a cubed, and you keep going, right? And that just goes forever and ever and ever. Now, if you want to take the derivative of that function, right, the derivative of it, since this is something plus something plus something plus something, you can take the derivative of each one individually. And they're all powers of x, aren't they? Which means they all qualify for the power rule. So look at what happens to each of these. What's the derivative of a constant? 0. Gone. What's the derivative? Forget C1's a constant, right? What's the derivative of x minus a with respect to x? It's just 1, isn't it? Because a is a number, right? So derivative of x is 1, derivative of a is 0. So derivative of that is 1 times c sub 1, so you get c sub 1. Now come out here. What's the derivative of this? C2 is a constant. What's derivative of something squared? 2 comes out, right? And then you reduce the power by 1. 2 comes out. C2 is the constant that was there, and then the power came down by 1, right? The next one would be the 3 comes out. C3, this to the second power. Do you see it? What's really cool about it, I think it's cool, is that if you take this original formula right here, now I want to do it, I wrote this really small, so I want to blow this up a little bit. There, that's a little better. I want you to notice that this formula up here in the sigma notation, if I took the derivative here, in other words, if I pulled the n here out in front, I would get n c sub n, wouldn't I? And then if I subtract 1 from the power, I get n minus 1, wouldn't I? That's this formula down here, isn't it? This blue line, the last one. The n came out from up here, and then the n minus 1, power went down. But there's a huge thing in here you have to pay attention to, and I highlighted it. What is it? It starts at 1, not at 0. Let's see why. Let's see why that's true. Let's say this started at 0, right? Let's say that this started at 0. Then what would you get? 0, right? Do you agree with that? All right. Come back over here. Let n be 1. Well, how can I? Trying to figure out a way that I can make this clear that it can't start at 0. Well, it wouldn't make sense to start at 0. Does that make sense?
Is the n multiplying times the whole thing?
Well, hold on. Yeah, the n is multiplying times everything, so it'd be 0. So you don't need that, right? You don't need to start at 0 because your first one's going to be 0 anyway. So when you go to 1, watch what happens. When you go to 1, you get 1 times c sub 1, and then 1 minus 1 is 0, so you get 1 times c sub 1, which is just c sub 1. And then when you go 2, it's 2 times c sub 2, x minus a to the first power. So we started at 1, not at 0, because it doesn't make sense to start it at 0 since there's nothing there. Does that kind of make sense? So when you see that in the formula, don't let it freak you out. Like, why the hell did it change from 0 to 1? That's the way, that's the convention, okay? Now, integration works the same way. If I want to take my original function and I want to find the antiderivative of it, right, the integral, the antiderivative, then I have to take the antiderivative of each term. So what do? What's the antiderivative of a constant? Antiderivative. The constant times x. What's the antiderivative? This is a constant here, c1. What's the antiderivative of x minus a? 1/2 x minus a squared. And then there's your constant in front. What's the antiderivative of forget the constant, x minus a to the second? 1/3 x minus a cubed. There it is right there with that constant c2 sitting there. So you see how that's going to work? So look at the formula down here at the very end. I'll blow that up so you can see it a little better. Oop, that's not blowing it up. Go a little bit bigger. That's a lot bit bigger. Does that look familiar? 1 over n plus 1. Remember that? That's basically the power rule for antiderivatives. So you take your series and you go, again, backwards. 1 over n plus 1. So you scale it and then you add 1 to the power. Also, where does the series start?
1.
This is, actually, I wrote that down wrong. Where should it start? What's my first term need to be? C sub 0 x, right? C sub 0 x. So this should start at what? 0. So that I get what? 1 c sub 0 x minus a to the 1, which would be c sub 0 x. I just realized that I wrote this down wrong. Come in here, right here. Do you see the c sub 0 x? It should be, well, x minus a, it doesn't matter. See, you're going to have your constant of integration. Let's do this. Just change this 0 right here. That's the only problem. Just remember that sitting out here, with all integration, you have a what? A constant. So the book throws in here a big capital C, right there. A big capital C. I didn't put it in there. Now let's see just how frickin' important this is. All right, let's go to a new page. So same instructions as earlier. Express. This is example 6, right? 5? 6, okay. Express f of x equals 1 over 1 minus x squared as a power series. I'm going to write this in red because it's wrong. I wouldn't write this down. You might be saying to yourself, oh, well, that's just equal to 1 over 1 minus x times 1 over 1 minus x, right? That is, right? That's the same. And you may be saying to yourself, okay, that's just sum n equals 0 to infinity of x to the n times sum n equals 0 to infinity of x to the n. Because aren't those both what we just looked at a second ago? Isn't it? That's not wrong, okay? That's actually correct. But the problem becomes, how do you actually turn that into a final, what we're looking for is a final answer that just has a single sum so that we can look at it as a power series. This is not a power series. This is the product of two power series. Do you see that? We want our function to be just a power series by itself. See, do you understand the difference of what we have and what we're looking to get? Not only that, how in the world would you actually multiply that? Isn't that 1 plus x squared plus x cubed forever times 1 plus x squared plus x cubed forever? Right? That's multiplication. So wouldn't you have to do 1 times all these plus x times all these plus x squared times all these plus x cubed times all these? Right? That'd be kind of crazy.
Can you square the n, or I mean the x?
Where?
I mean, if you're multiplying each other by itself.
That's a really good question. Can you like put them together and make it like x to the 2n or something like that? You cannot. That's a great question. Can you combine these two together since it's multiplication? Can you make it this? X to the n and then something like squared. Is that true? Let's convince ourselves whether or not that's true or not. Are these two things the same? I'm going to leave this here, okay? Because that's what it really means, right? That's what it really means. Write out the first few terms of this. What would you get? So let n be 0 first. What do you get? I'm doing this one right here. Let n be 0. What do you get? 1, right? X to the 0 is 1. 1 squared is 1. Okay, 1 plus. Now let n be 1. What would you get? X squared plus. Now let n be 2. X to the 4th plus x to the 6th plus. Okay, that's what you would get if you did this. And I said you can't, right? Do you see why this is not right? What am I missing? I don't even have, like, if I did this multiplication, 1 times 1, I get what? 1? 1 times x, I get x. I should have an x in here. 1 times x squared, I should get an x squared. I do have that. 1 times x cubed, I don't even have an x cubed. So that is not an algebraic property of sums. If you have a sum times a sum, you cannot just make a single sum out of that and multiply the insides. So I'm glad you asked that question. Was there something else? So this is not going to work, okay? This is not going to work. I'll leave it there, but I'll put a big old through it. Let me get back to the problem we had. What was it? F of x was equal to, did I write f of x up there? Yes, I did. 1 over 1 minus x squared. Now, check this out. I just realized when I looked at this, I was like, well, wait a minute. Hold on a second. Hold on a second. Isn't this equal to the derivative of 1 over 1 minus x? Isn't it? So maybe we need some help here. Let's look at this right here. 1 over 1 minus x is the same as 1 minus x to the negative 1, isn't it? What's the derivative of that? So you have to do chain rule. Take the derivative of this for me. Negative 1 would come down, right? So I'm taking derivative with respect to x. Ooh. The derivative with respect to x would be negative comes out in front, negative 1, and then what? 1 minus x to the negative 2 times chain rule, go inside, take derivative of what's inside.
1.
Negative 1, right? The negative in front and the negative in the back cancel, and you're just left with 1 minus x to the negative 2, which is 1 over 1 minus x squared, right? So this function that I'm looking at right now is actually the derivative of that function. Questions? This is great. Goosebump time. Therefore, my function is equal to 1 over 1 minus x squared, which is equal to the derivative with respect to x of 1 over 1 minus x. That's what I wrote earlier, right? But what is 1 over 1 minus x? That's a power series, isn't it? That's power series. That's the one we started class with, the big time one, isn't it? So can I say that my function f of x is equal to the derivative then of that series n equals 0 to infinity of what? X to the n, right? So my function is the derivative of a power series. And the derivative of power series can be done term by term, right? So, or I can just do the derivative on the formula itself. How would you take derivative of x to the n? N, x to the n minus 1, right? But whenever we take the derivative, something else has to happen. Hold on. Let me see here. F of x equals sum n x to the n minus 1. I left it out intentionally. What is it? That's antiderivative. N equals 1, right? N equals 1 to infinity, not 0, right? Now, can you help me by writing out a few of these terms? So where are you going to start?
1.
N equals 1. You get what?
1.
1, right? 1 times x to the 1 minus 1, so 1 times x to the 0. That's 1. Okay, next one plus. Now let n be 2. 2 x, right? Plus 3x squared plus 4x cubed forever, right? That's the power series for the function up here. That's this expressed as a power series. So what we did, to recap this, is we noticed that what we were looking at was the derivative of something that we know the series for. And then we took the derivative of that series. Make sense? So there would be, I mean, this is basically the answer right here. but this is me writing out a few of the terms. Now, I'd like to do something before we move on to the next example that you're gonna see come up a little bit later. I'm going to do what's called a change of index. Okay, understand please that what I have highlighted in yellow is correct. There's nothing wrong with that answer. But I'm going to change the index, and what's going to happen is a lot of times later we're going to want this x to the n minus 1 to be an x to the n. We're going to want it to not have an n minus 1 up there. So what I'm going to do is this change of index. I'm going to replace n with, let's do n plus 1. All right, now what's going to happen if I do that? Let's see. Everywhere I see an n, I'm going to replace it with what? N plus 1. So my function f of x equals sum, not n equals 1, but I replace every n with n plus 1. So n plus 1 equals 1 to infinity of not n, but what? N plus 1 times x to the n plus 1 minus 1. Now let's see what effect that has. Look at this lower limit of my index here. N plus 1 equals 1. Isn't that an equation? Solve for n. Subtract 1 on both sides. N is 0, right? Yes? So sum n equals 0 to infinity. N plus 1 x to the n. Now my question is, how much have I changed here? I mean, I've changed it. Instead of going from 1 to infinity, I now go from 0 to infinity, right? I've changed the power from, instead of it being x to the n minus 1, it's x to the n. But I've also changed the number out front to an n plus 1. Does that give you the same series? Start at 0. Plug in 0, what do you get? You get a 1 here. X to 0. So you get 1. Let n be 1 now. You get 2x. 3x squared. So changing your index does nothing as far as changing the series. All it does is allows you to manipulate the way things look. Because in a little while we're going to be taking two series and trying to add them together, and we want all the x's to be to the same power when we do that. I want to know what class that is over there. I'm freaking listening to music and stuff, man. Is that Cal 3 over there? I think it is. Am I on 7? We should go over there and do some Cal 3. All right, let's look at this one. F of x equals natural log of x plus 5. Same instructions. Express this as a power series. What's that? The derivative. We know something about the derivative of that, right? Let's write that down. The derivative of this, right? The derivative of this function is 1 over x plus 5, isn't it? Right? That means that that's the same as 1 over 5 plus x, which is the same as 1/5 times 1 over 1 minus negative 1/5 x. What the hell just happened there, right? What am I trying to do? I'm trying to get it to look like the big time formula, right? See, I look at the 1 over x plus 5 and I say, look, I can make that the big time formula. So I'm going to be able to write that as a series. Now I'm not writing the function, right, out as a series, right? I'm writing its derivative out as a series. And why is that okay? If I write out the derivative of a function as a series, what can I do to get back to the function? Integrate it all back up, and I can get back to the function. You see that? I'm going to look at its derivative as a power series, and then integrate it back up to get to the function itself. But I first have to be able to rewrite it as its power series. So what is that as a power series? So the derivative is equal to 1/5 sum. Oh, that's a weird sum. It's one of my more interesting looking ones. N equals 0 to infinity of what? Negative 1/5 x to the n. Any questions on that? Now, before you integrate, what I recommend you do is let's look back at this formula for the term-by-term integration and differentiation that I've gone past here. For the formula, where is it? It says that if you're going to do term-by-term integration or differentiation, you have to have sum n equals 0 to infinity of all your powers of x by themselves, and it has to be x to the n. And then your c sub n is the constant out front, all right? So what we need to do is get all our constants and everything else out front and get our x to a power by itself. Then we can integrate. So back to where I was, right here. So how can I do this? Isn't this the same as sum n equals 0 to infinity? Can I take that 1/5 inside? That 1/5 here, move it inside? Yes? And I can make it a 1/5 times a 1/5 to the n times a negative 1 to the n times an x to the n. Okay? What I want you to recognize at this point is that everything out here that doesn't have the x in it, that's my c sub n. And this right here, of course, is like my x minus a to the n, right? So that's what I needed before I could do integration. And when you do integration, all that green constant stuff doesn't get touched by the integration. The only thing that happens, and I'll write an example right here, like if I asked you to take 8x to the third and I ask you to integrate that, well, 8's not a good one. Let me do 18, okay? Then you don't really have to focus on the 18, do you? You cover up the 18 and you say what? Antiderivative x cubed is 1/4 x to the fourth, right? Then you bring in the 18. That c sub n in front, when we integrate, is just a number, isn't it? It's just a number, so I don't care about that. What I care about is this, because I'm integrating with respect to x. But you have to get it to look like that first. So now go ahead and do the integration. Let me see if someone can tell me what the next thing should be. This is f of x, f prime of x. Let's see if anyone can go out on a limb here today and tell me what they think I should write next.
As far as what? The antiderivative?
Well, yeah, like if you were me sitting up here writing the next line, what would you write to?
Class dismissed or please.
1 over n plus 1, x to the n plus 1. What about all that c sub n?
Put it on top. So all that stuff over n plus 1.
All that stuff over n plus 1,
X to the n.
x to the n plus 1. That's correct. A little more though, we need the sum in front still, right? What about the left side? The integral, right?
Be f of x, right?
The integral of f prime, which is f, right? But I'm going to write it down. So this is what I was trying to get to. You have, I'm going to now take the antiderivative on both sides. The antiderivative of f prime of x equals the antiderivative of the sum n equals 0 to infinity of, check me out, 1/5 to the n plus 1 negative 1 to the n x to the n. So the only thing I did here is I put that 1/5 and 1/5 to the n together. They were so sad to being apart, so I put them together. And all I did was threw the integral sign in on both sides. So I'm going to integrate, because if I integrate this side, integrate the derivative, you should get back to f, shouldn't you? So now my left side's going to become f of x, which is what I want. And now I do the antiderivative of the right side, which is the sum n equals, do I go to 1 or 0 on antiderivative? It should be 0. Were my notes wrong? For derivative, it's 1. Let me make sure my notes were right. Yeah, it's 0. That was the thing I said to fix, right? I said fix that. That should be a 0.
Oh, really?
Yes. The only time it switches to the 1 is when you do the derivative of the series. Okay, so I'm going to go n equals 0. Now, I like to do it this way. 1 over n plus 1 times, now all that junk that's still there, 1/5 to the n plus 1, negative 1 to the n, but now x to the n plus 1. So the two things that kind of appeared in here, you had to introduce the 1 over n plus 1. So from this sum right here, you introduce the 1 over n plus 1 and then the x to the n plus 1. So there's your antiderivative, isn't it? Everything else is just a constant sitting in there. I'm looking right now to see if I did anything. I didn't do anything else to it. Nope, that's fine. Now, can you give me a few of these? Can you write out a few of the terms of this? So start at n is 0. 1. Maybe I'll write it out. 1 times 1/5 to the 1, because I'm plugging in 0, right? So 1/5 times negative 1 to the 0. 1 times x to the 1, which is x. So my first term is what? 1/5 x. Okay, my next one's going to be negative, isn't it? Because it's alternating. So it would be negative, see, I'm plugging in 1, I get 1/2 times 1/5 squared is 1/25. I already took care of the negative 1 to the first power, x to the second. So minus 1 over 50 x squared. And so on and so forth. Yeah, plus 4 dots. Start a new math, a new revolution. I think we have time for this last example. Let me see here. Okay, I'm going to try and do 2 examples. This one I'm only going to set up for you. I'm actually not going to work through the whole thing. Example 8. Same instructions. express this as a power series, x plus 2 over 2x plus 1 times x minus 1. Ah, man, I kind of presented the problem wrong. I'm sorry. Oopsie. Oh, man, what an ass. This is the way the problem was supposed to be given. My apologies. Okay, so the first thing you have to do after this step, okay, so this you want this as a power series. So the first thing we do is we factor this out. And then well, I don't know why I'm doing that. Let me go back up to this real quick. Let me just show you the work. Here's the problem right here. Okay, so there it is. So you looked at this right here. From here, remember, I'm going to send all these notes out, so you don't need to write this down. Took this, factored it. Partial fraction decomposition allowed me to turn this into these two. These two can be written out as the big time formulas. If you just move things around and mess with the signs a little bit, you can get this one to be a power series, this one to be a power series. Since they both start at 0, this is x to the n. This one over here becomes negative 2x to the n, which turns into a negative 2 to the n, x to the n. Since they both have x to the n, since both of these start at the same place, I can put them together into one sum, and I can factor an x to the n out. Does that make sense? And then from there, you're done. And then you can write out the first few terms. So that requires a little bit of partial fraction to begin with. The thing that should trip you off to this is that you can't really do anything to this. Like, it's not like the previous problem where you say, oh, natural log derivative of that was something, or it's not the one before it where we said, oh, that's the derivative of something. Let's go backwards with it. So, all right, let me get to this last example. I wonder if I can try and walk you through this one. Can I try and walk you through this one just for time's sake? Or do you think I'm being too ambitious? Tell me what you think. Walk you through it? Okay, then let's make sure we really understand it. Express this as a power series, okay? So the first thing that I do here is what? What did I do?
Oh, that's right. Separate the.
I just split it into two fractions. Since I had two terms on top, I did two fractions. The x squared over it, the x over it. Okay, now from each of these, let's look at these individually. This first one, x squared over 1 minus x quantity cubed, right here. I can look at that x squared out in front, right? And then this 1 over 1 minus x cubed. I'll deal with that in a second. Then this one, same thing. Pull the x out front, 1 over 1 minus x quantity cubed again. So if there's a way I could get both of these is series, then all I have is an x squared in front to multiply through and an x to multiply through. Is that all right? Notice that the 1 over 1 minus x cubed is the derivative of this. Now, I'll write that down on the board so you can see what it is. It's 1/2 1 minus x to the negative 2. Isn't that what this middle one is? That's what that is? What's the derivative of this? Negative 2 comes out, becomes a negative 1. 1 minus x to the negative 3 times chain rule inside negative 1. The negative 1 and negative 1 cancel, and you get the 1 over 1 minus x cubed. So the 1 over 1 minus x cubed is the derivative of 1/2 this. Well, what's this?
Which one?
This one right here.
Oh, we just did that one.
We did that one, didn't we?
Yeah,
A second ago?
Derivative of the power
So I did that a minute ago. You have to go back up and look in the notes. I did that one right, where was it? Right there. See that problem I did earlier? That's the problem I did earlier, isn't it? So I had to create that power series. And how did we do that one? We said, oh, but that's the derivative of something, right? So we've already done all this work. And we got to this answer right here. Look at it. Sum n equals 1 to infinity x, right? That's what we got right there? Yay, yay? Okay. Also, I could change the index on this. If I wanted it to not be x to the n minus 1, if I wanted it to be x to the n instead, I could change the index by replacing n with n plus 1 on this. If I replace n with n plus 1, I do the work, and it becomes this one right there. Is that okay? Let's go back to the problem. Where was it? Okay, so we were here. This is the derivative of this, right? Which is 1/2 times, well, it's the derivative of 1/2 times whatever this is, but this is the power series we just found up in the previous example. Notice the index is at 0, and that was it right there, right? So can you take the derivative of this? Well, how do you do it? This is the number in front, right? X to the n. How do you take derivative of x to the n? N comes out, subtract 1, and the index changes from an n equals 0 to a what? N equals 1. So the n came out, the n plus 1 was still there, x to the n minus 1, and then the 1/2 is out front. So this is the series for this. Yeah? And then what did we have? It was here and here. So let's look at this first one right here. I have an arrow. The red one is actually this first one right here. And, well, I don't even know if that's what it is. No, I did them both the same. No, what the hell did I do? Yeah, no, I did them both at the same time. This whole line is right here. So let's see. X squared there, right? Here's this whole series right here. This thing right here turns into this series. So 1/2 n equals 1 to infinity, n times n plus 1, x to the n minus 1. Then I have x, which is here, times 1/2, and then there's that series again. Got it?
Okay.
Now what? X squared gets multiplied in here. When I take x squared in there, don't I add the exponents? What's x squared times x to the n minus 1? That's x to the n minus 1 plus 2, which is where I get this n plus 1 from. Everything else is the same. Then this x goes in, and you add 1 here, and you get what? N. Do you see it? I know this is a lot for me to talk through, but okay, now I want to try and put these two sums together into one sum. The problem I have is that right now, this is x to the n plus 1, this is x to the n. I'd like them both to be the same. So the only way to make them the same is to somehow change the index. So let's see what I do here. If I want to take that and make that an x to the n to match the one on the right, I need to take one away, don't I? So what I do here is I make exponents on the x's the same. I change the index by switching my n to n minus 1s. So if I come right in here, right there, and I replace that, if I replace the n with n minus 1, and move that to the move the 1 to the other side, I get what? N equals 2. And if I change the n's to n minus 1s, this n here becomes an n minus 1. The n plus 1 becomes an n. And then the n plus 1 here becomes an x to the n there, right? Now I've got x to the n there. Over here, I don't need to change anything because it already has x to the n. But now I have another issue. This index starts where? 2, and this one starts at 1. So how am I going to resolve that? what I do, where was I? Here's where I was, right? Oh no, here's where I was. I changed the index, right? Now I have the same index. What did I do here? If this one starts at 1, then the next time, right, it starts at 1 and then the next time it'll be at 2, right? So can't I just, what would I get if I plug 1 in right here? 1 plus 1 plus 2, right?
Yeah.
1 times
2.
2 times x, right?
The 1/2.
Times the 1/2 out front. So wouldn't I get 1 times 1/2 times 1 times 2 times x? That's the first term of this guy, right? Plus the second term, right? So what I do is I peel that first guy off. I say, okay, let me get the first guy and peel him off. And now I sum it from 2 to infinity. See, the first guy's already taken care of. He's here. That's a critical thing. Do y'all get that? Now these have the same index and they have x to the n's. So I can put them together. So when I put them together, they both have a 1/2 in front of them. Here's the sum, and all I do is I put all this junk plus, because it was a plus sign between the two sums, all this junk here. Then all that stuff that I peeled off is just an x out front, or out on the side. Now I choose to put the x in front instead. Instead of leaving it out at the end, I threw it over here. And what did I do on this line here? What did I do right here? What did I do? I pulled out the x to the n that appears in both of these terms. And then what do I do from here to the next line? I distributed n through, so I get n squared minus n plus n squared plus n. And when you put that together, you get 2n squared. Then you have the x to the n that you pulled out. What do I do from here to the next line? Put the 1/2 inside, killed off the 2. So I've got this. What do I do from here to here? Well, this doesn't always work, but it works in this case. If n equals 1, what would happen here? If n was 1. My actual index starts where? At 2. But what if I had said let's start it at 1? What would you get? 1 squared times x to the 1, which would be x? Holy shit, that's it right there, right? It just so happens that x is what I would get if I had started this with 1. Got lucky. So I just changed it from 1 to infinity, and that is that. Won't always happen. Because if I look at this right here, this n equals 2 to infinity, n squared, x to the n, I'm going to start it at 2. I have to, because that's what I did. But if I did start it at 1, what would I get? If I started that at 1, I would get 1 squared is 1, x to the 1 is x. So this would just be an x. Well, that's what I actually want. I want this thing plus x. So if I start that at 1 instead and get rid of this, that would give me the x for the first term. But again, that's lucky. And then this is the first few terms.
That's like winning the lottery.
That's a tough problem right there. Okay, there's a lot going on in that problem. Okay, for your homework,
Do that problem twice.
obviously you need to do what we did last class. You know, the last homework assignment, you need to have that done. But I'd like for you to do 3, let's see. I started doing the homework myself. Let me see how far I got. I only got to 11? No. I did more than that. Okay, well, your assignment's going to be 3 through, I'll try and be somewhat nice, 17 odd. 3 through 17 odd. I think that's good. It's a lot of work right there, all right? That was on page 474.
Anybody need one of these?
All right, everyone, that was fun.